And hello, welcome to this video. So this video we're going to talk a little bit more about Labview. So last time I think we were talking about how to get transfer functions tested with a case structure. So we have a case structure. Okay, case structure. Let's see whether I can write this properly. Case structure. There you go. Okay, so that's that will allow you to select various sorts of transfer functions, and you can wire it out to graph output, so-called. You can wire it out to a step response, and you can even do a Bode plot. Okay, Bode plot, which will typically look like this for the magnitude plots, and you have phase plots as well. So you have Bode. You have step functions. You can even look at the equations or graphs, whatever graphs they are. So that's what we did. Okay, now moving on to another interesting bit. Okay, I think the last time I also said something about poles and zeros. Okay, so theoretically you can do something with poles and zeros. Okay, this is the next part, next VI. But before I go on to this next topic, let's talk about poles and zeros first. Okay, so again, if we have this transfer function, we go to some second order, we can see the poles and zeros being put here, and you can use the engineering display so that you can see which poles and zeros there are very easily. Now you can even use poles and zeros to make a transfer function. Okay, I said that the last time. So if we go to the block diagram, you should be able to see all of this here. Okay, we can actually use a poles and zeros to define a transfer function. So I'll just do it here. I'll not do it in the case structure. Okay, let's see. Where's your control and simulation? Go to control design. Control design. You go to model construction. Okay, once you go to model construction, you'll see this thing called CD, construct pole zero gain model. So click that, put it here. Okay, so you'll be able to define the poles. You have a one for zeros, one control for poles. Okay, you can even control the gain. Okay, and your output, you can use this, what do you call that? Draw, control and simulation. Go to model construction. So I'm assuming you're very familiar already. So I won't let you be bored by too much long-winded instructions. If you're not sure, please go back to the older videos. So we can draw the transfer function, and we can create this indicator, which is some equation over here. And alright, so with all these, your poles, zeros, and gains will appear here. And this is the poles and zeros equation. Okay, it's all over the place, so you need to drag it here. Now, okay, let's save and play. Okay, let's say you want a gain of 5, and your transfer function will be just the number 5. Okay, let's give a pole of maybe s minus 3. Okay, minus 3. So s plus 3 will be at the bottom. You want a pole of minus 5? Okay, you will have this s squared plus 8s plus 15. Okay, so this is your transfer function equation. No problem, right? Now, problem is if you want your poles to be complex. So let's minus 5 plus 2i. Okay, the whole thing will crash and stop. Why? Because over here it says control design and simulation, hex 0x fff blah blah blah. One or more of these complex numbers does not have its complex conjugate. Meaning to say, if we have this minus 5 plus 2i pole, you should also put a minus 5 minus 2i pole. Okay? But the thing is that you can't write these two poles at the same time, right? You can't write these two poles at the same time when you're running this in real time. So while this is good if you want to slowly, think about how to write your transfer function, it is not good for doing it in real time, because every time you want to put a complex root or complex pole, it's going to just give you some error. So that will not happen with this version of the transfer function. So you have a custom transfer function, and then you can just add the numbers and the quantities in real time. So no problem. Okay, so you can just keep adding and adding and adding. It will not give you error. Of course, you can actually get what you call it, unstable system, but you'll not get this kind of pole zero error. Okay, so that's one thing why you don't want to use poles and zeros to construct your transfer function if you're running in real time. If you're not running in real time, then this is perfectly fine. Okay, it's perfectly fine. All right. Okay, let me pause. Okay, so it's about 6 minutes in. Okay, I still have time. Let's go on to the next topic. Okay, so let's say you have a control system. Okay, you have a control system. Okay, and you have all your transfer functions ready, and you kind of know they are stable. Okay, you have a transfer function, you know it's steady, and you want it to be stable, right? And let's say you have some input signal, okay, from Labview. Okay, let's say this could be a thermostat, right? This could be a thermostat. Okay, and you want to use it to control a heater, right? I mean, there are tools for this. Okay, there are tools for this. So if you want to develop a control system, the main way you would do it is with the use of the PID controller here. Okay, you have this whole suite of PID controllers right here. Now that is enough if you, let's say, want to design a simple thermostat. However, let's say you are running something a little bit more complex, and let's say you are trying to you're trying to simulate a process. Okay, so let's say you have a chemical reactor. Okay, some because I do chemical engineering, right? And the main thing we want to ensure is that our, for example, reactors are steady. Let's say there's some packed bed reactor. Okay, let's put some fillings in here. Some packed bed catalytic reactor. Okay, so you have some chemical going in at Ca0. Okay, some chemical going out Ca. Okay, whatever concentration it is, I don't know whatever reaction it is. However, something the reaction rate, equals to some function of temperature at a constant flow rate. Of course, if your reaction rate is at some function of temperature, okay, so you kind of want you know that if your feed is going in at some temperature T1, so this feed will actually contribute to controlling this reaction rate, right? This feed temperature is going to control the reaction rate. So okay, if let's say you have a heater here, this will actually, this system will actually control this feed temperature. And feed temperature will go into here where you have a catalyst or something going on, and this is a continuous flow. You have some feed going in, and some catalyst is reacting with your reagent, and this reaction rate is heavily influenced by temperature. So depending on how you influence the feed temperature, your eventual how do you say, a few things will be affected, right? Your eventual concentration here will be affected. So this Ca is some function of inlet temperature, right? So I call it Ca is some function of T1 and some other factors as well, we do not know. And of course, your reactor temperature is also some function of T1. What are the actual relationships? We don't know, but it's very convenient to use transfer functions to, let's say, determine the maximum reactor temperature as a function of T1 to see whether it's stable. So if you adjust your feed temperature, your reactor temperature will also change. Okay, your reactor temperature will also change, and you want to ensure that it is safe. Okay, so if you want to run some real-time simulation and you adjust T1 such that it affects the reactor temperature, you might want to use some transfer function here, right? You might want to use some transfer function here. So if you want to run this kind of simulation, how are you going to do it? Okay, so good thing for you, Labview has this this palette called the simulation module. Okay, so this is the example of how it looks like, the simulation module. You can actually give a time varying input, and based on a transfer function that you customize, it can give you some time varying output. So no problem, that's what we want. And this is one of the examples. Okay, so as okay, so I have some extra tidbits over here, but you will be able to find this sort of example in your control and simulation. Under simulation and signal generation, you have a sim-x sine wave. So your sim-x sine wave is all that's over here. This other part I will go through later is something I added. Okay, so what this does is that it takes a sine wave, it puts it through a transfer function, and then it gives out another sine wave. Okay, so again, sine wave, a sine signal. So this is your input signal. It goes through a transfer function and it gives you some output signal. Okay, so you can see that over here, there's an input and output sine wave. Okay, I'm gonna stop. Okay, the gain is 1, and well, it's 0.5 s plus 1. That means the process time is 0.5 seconds. It's a first order kind of a thing. Of course, if we introduce more filters, we can change the transfer function as and how we like. Let's say let's give it more over here. Okay, so this is some transfer function hs. Let's see whether this thing is stable or not. So I have no idea whether this thing is stable, but this transfer function, you know, it could be this reactor. Okay, it could be this reactor system where you have some inlet temperature. So it is connected through a transfer function which takes this inlet temperature, time varying inlet temperature, and it gives the output, which is maybe your reactor temperature, because you want it to be within some safety margin. So if you want to simulate this, you can, okay, using this simulation block, this simulation loop. And if let's say you have lots of other stuff in your Labview, okay, if you want to access these variables outside the simulation block, you'll need to use something else called a access model hierarchy. but don't worry, we'll get to that part later. Let's just deal with simulation blocks first. Okay, so for the most part, these time varying signals, you cannot bring them out into the what do you call that? The rest of your block diagram, because it just won't read properly. There's a proper way to do it with the access model hierarchy. So just want to put that in your mind first, but we'll come to that later. So this is a quite important thing. That's why I want to emphasize a lot of it. So do stay tuned. We'll look into that part later. Okay. So how does this work? Okay. Well. Okay. I mean there are some good references and tutorials. I put all of these inside the description. Okay. One of them, I mean, there are a few here, and I'll copy and paste all of this into the description, so don't worry about it. Yeah, but the thing is, where you can start is just to start opening one of these Labview examples. So go to your Labview folder under National Instruments, go to Labview, go to Examples, and you go to your Control and Simulation. Okay, go to under Simulation. You will see something called signal generation. Okay, under signal generation, you'll see SimX sign. Okay, this is the original example, which is not tampered with. If you press play, okay, you'll see these signals being generated. You can adjust the amplitude. Okay, and you see that the top and bottom will differ. Okay. Okay, 17 minutes in. Yeah, the top and bottom will differ a little bit, but you see this first part is the input. The second part is this output, related of course by some very short transfer function, very simple first order transfer function, which you can see in the block diagram, 1 over 0.5 s plus 1. So it's a stable system. Okay. So if we change the frequency here, we can change it in real time. If we change the phase, we can also change the shape of the graph in real time, which is very nice. This is what the simulation suite allows us to do. Okay, so let me stop. So that's the demo. How do you construct something like that, and what does each part do? Okay. So let's see. Right. Yeah. So let's do something simple first. Okay, I'm not going to play with this block diagram. Just the demonstration. And neither am I going to do this. Well, we'll start from scratch. Okay, so it's easier. So this is where we were previously, but we'll have a new VI, right? And we'll call this VI. What do you call that? Demo YouTube CD control simulation generator. Okay. Alright, so quite simple. Okay, how do you start the whole simulation loop? Because just now you saw this yellow box thing, and that's actually how you actually start your simulation loop. Because if you actually go to simulation, you go to signal generation, and let's say you want to get a sine wave, you can't put it anywhere inside this control block diagram. So first, what you need to do before you start any simulation is to go for this control and simulation loop. So if you're familiar with while loop or case structure, it's very similar. So click on this control and simulation loop, and you drag it across, and that's where you have your simulation loop started. Okay, so your simulation loop must start like that. Okay, it must start like that. And what do you do within the simulation loop? Okay, for example, you can go to simulation. So under control and simulation, go to simulation, go to this signal generation, and the most simple, of course, is a sine wave. So let's put this sine wave in here. Okay, the sine signal is where you can't really put in any outputs or inputs by default, but what you can do is create some indicator, which is a number here. Okay, not the most helpful, But if we look at, we can actually check what tools were being used last time. Inside this block diagram to see what they do. Okay, so they actually have this array building thing, and then you have this waveform chart. Okay, so you have a waveform chart over here. So let's put in a waveform chart right there using this. We'll try to find what this thing is. Okay, so we'll not use the default output, though I mean that you can do. We want to see a waveform. So let's try looking for a waveform. I'll look under simulation, signal generation. Okay, hold on. Oh, it's 20 minutes already. Okay, let me try to finish this part and we'll call it a day. So let's see. You go to control and simulation, simulation, and you go to graph utilities. So there's this thing called sim time waveform. So look for this thing called sim time waveform. Okay, and what it will do is it will output a waveform chart. You will be able to see this waveform chart over here, no problem. Okay, before that you will need to start making an array, because this thing will actually put a real-time signal out. What you need to do is take an array. You go to this thing called build array, put it here. So connect the output of your sine signal into this array builder. So if you're not sure, go right click, go to array. You'll see this thing called build array. So this thing should be quite familiar to you by now. Okay, then you connect this array into this waveform chart thing, this waveform chart builder. So we'll save it and let's see whether this basic thing runs. So you can see there's a sine wave thing here. Okay, so this is sort of running, not really real time and all, and it looks very jagged for the time being. Okay, so how do we actually deal with that? I think we'll just talk about that in the next video. Okay, but yeah, I'll stop for now. I'll get back to this later, since we are like running low on time. So thank you. I'll see you again. Bye bye.